Hello everyone, this is No Mustafa, and I did the rocket next option compared to the other options. And this is my main function. And before I show the main function, I want to talk a little about what rocket motion is, just a little background information. Rocket motion is based on Newton's third law, which states that for every action there is an equal and opposite reaction. Hot gases are exhausted through a nozzle of the rocket, and they produce the action force. The reaction force in the opposite direction is called the thrust force, okay? And the thrust force just causes the rocket's acceleration. So we let the initial mass of the rocket be m, and then its initial velocity be v. In a certain time, delta t, the mass of the rocket decreases by delta mass, delta dm, as a result of the fuel combustion. This leads the rocket velocity to be decreased by delta v. And that's just a little background information. Here in my function, I didn't particularly spend much time in here because it's all just naming variables for the computer to figure everything out. We're down here, and so this is just making sure the fuel mass doesn't go below zero, because you can't have negative fuel mass. And if it's not below zero, you run this. I like to think of this as the kinematic equation. It's the fuel mass equals the initial fuel mass minus delta m, just to like the fuel mass final equals initial mass minus change in mass. It's like similar to that kinematic physics equation, delta t equals t final minus t initial. And then here it's more kinematic equations. The velocity, final velocity, the next, well, in this case, the next velocity equals the initial velocity plus acceleration times delta t. This is height equals initial, the next height equals the initial height plus the initial velocity times delta t plus a half acceleration delta t squared. And this is making sure the height doesn't go below zero. And this is another kinematic equation where the next time equals the initial time plus the delta time. Okay, and I just want to say I wanted to use a for loop here, but it was kind of difficult. I couldn't figure it out, so I decided to do conditions here and then just call it another function. Have this be a subfunction in another function for this rocket trajectory. So it calls it here. You see rocket next, and it's just making sure because this is just from one point to another point. It gives you one point, which is the starting time, which would be like 0, 0. And then the next point, which is whatever delta t, however much time you go to. And it'll give you all the initial conditions there, like the velocity and the height. But it's not giving you everything in between. And this rocket trajectory gives you everything in between. So on to the next one. This is the test rocket next. It passes. Everything passes, thankfully. And I'm going to talk to you guys about the simple one. So this is basically like a by hand, okay? The change in time is going to be 1 here. You use a struct because it's very important to use a struct. It wouldn't work otherwise. There's a lot of initial conditions, and the fuel mass is going to be 90 in this case. The rocket mass is going to be 10. Everything else is the starting conditions. The initial condition is going to be 0. There's no velocity. There's no height. There's no linear drag or quadratic drag. There's no ratio of fuel burn to impulse, and there's the thrust, the force of thrust. This is what the F of t is. It's a function handle, and it's 2000 in this case. And as you see, the time goes 1 from the change in time because it starts at 0 to 1, and then it gives you the velocity and the height, and the condition and the absolute. All this right here is just making sure that it's equal. The actual and expected is equal to each other, and then the tolerance is making sure with all these decimal points are not going to throw the computer off. And then well, yeah, and for people who don't know, and then I just asserted it. And then for people who don't know what the percentage is, it just means there's no in between zeros in the decimals. Just something to help the computer understand this and not throw it off. And then we can go right ahead to the animation, and here it's just showing with set conditions how high the rocket will go until it loses thrust and fuel combustion, and then just goes all the way down and lands back. So here with a mass of 100, no linear drag. There's a small quadratic drag, and the ratio of the fuel burn to impulse is very small, and there's an initial thrust of 5,000. And the max height was about 130, something like that, over like 7 seconds. Here this is, and it lands back down in a total of time of 14 seconds. So then lastly, it's the documentation, and Rocket Next just finds the next state of a rocket given the parameters of a current state. The syntax would be state equals rocket next initial delta t. It must be a struct by the following parameters. So this is the initial fuel mass, rocket mass, velocity, height, linear drag, quadratic drag ratio, fuel mass to impulse, fuel burn to impulse. Sorry, not fuel mass to impulse. The force. This should be a function handle, and it's just the force of thrust, and then this is the initial time. So quick description is the state of the equals rocket next and dt. It returns the structure parameters, each updated from its previous state, determined as a function of change in time, delta t. So the state fuel, this is the fuel mass at time t. It'll change as fuel burns off, rocket mass without fuel, and then velocity and the height at time t, and then the linear drag and the coefficient of linear drag and quadratic drag, and then ratio fuel burn to impulse. And then this is a function handle, remember, force of thrust, and then state, the current time, depending on how far, delta t. An example here, you call the initial is this, where it's 90, 10, 2000. This is from the by hand again, and this is what you get for your next state, as we saw before. So going into more into theory, it's like all particles, they behave in second law, as I stated in the beginning. So the sum of F equals ma, mass times acceleration, equals force, sum of force. So after adding in the forces acting on the rocket, this becomes math, just the force of thrust plus the force of drag plus the force of gravity equals mass times acceleration. Excuse me. If drag takes a linear dependence on velocity, then it would just be the force of drag equals the negative coefficient times velocity, the negative coefficient times velocity. If the drag over is quadratic, then the math is this: the force of drag equals the negative coefficient times velocity over velocity over left vertical velocity over right vertical velocity. And since gravity depends on height of the rocket math, this becomes the next equation that you just have to solve for to get your gravity, or whichever you want to do. You can use simple algebra. And then since the rocket is burning fuel, there must be a ratio of mass lost to thrust, which is calculated by the change in mass equals the force of thrust times the ratio of fuel burn to impulse times the change in time. And these are the state parameters. These are just some more of the equations we needed to do to make sure we get the right next velocity, height, mass, and time. And it's just, as I stated before. That'll be all. Thank you for taking time to hear my presentation, and you guys have a good day.